For today, but realistically probably also a big part of tomorrow, we'll be studying a quantum field theory known as the nonlinear sigma model. So it's going to be a little bit more advanced than the lecture so far. So today it's going to be a little bit more challenging. If you follow today's and tomorrow's lecture without any trouble, yeah, I think you can say you know quantum field theory well. Otherwise, if it sounds a little bit hard, it is a little bit hard. So try to follow, try to stop me with questions, but it's going to be a little bit more challenging today and tomorrow. Then the level is going to come down again. So it's kind of a parenthesis, what I want to do about the nonlinear sigma model. The nonlinear sigma model is a beautiful model that is classically conformal. It's an action that you write the action, there's no scale. So it looks like a conformal theory. It looks like a theory that has no scale, that is invariant under local dilatations. But then quantum mechanically, it's not. It's just classically. So classical, fine, yeah, there's no scale. But quantum mechanically, there is. And it's quite an interesting model. And it's interesting to learn how to deal with this quantum field theory. Okay, so that's what we are going to do. It's opening a parenthesis. Later, we are coming to this model at the very end of the course. But for now, it looks a little bit like a parenthesis that I want to introduce because I want you to have some time to play with ADS on your own. So please don't forget, do the tutorial and the homework before everything related to ADS. Do it before next Thursday. Okay. So let me first make one small comment before starting, which is suppose I have a free scalar. So this would be the coupling, not free, sorry, a weakly a scalar and then a phi to the 4 interaction, right? And now notice that this is equivalent if we rescale the field, phi equal 1 over square root of lambda phi hat, then this action becomes 1 over lambda, parenthesis, d phi hat square plus phi hat to the 4. So this is equivalent. It's just a different way of writing the action. But because people often get confused, I just want to write it in this way and stress that small coupling, you see, is equivalent to big factor in front. So small coupling, lambda to 0 is free. You see, when you consider this type of normalization where you put the coupling in front and then everything's of order 1, small coupling means big factor in front. Okay, so that was just a small remark. Okay. So let me then introduce what's called the ON nonlinear sigma model. Okay, and as I said, we are going to spend maybe an hour and a half on this model. So this model is the following. The action is going to be, there will be some coupling in front. Let me write it. So this would be the coupling. Again, it's in front, so when it's small, this factor is big. So this is 0 would be the coupling, and it should be small. And then there is an integral. It's a two-dimensional model. We are going to consider d2x. And then the action is just d mu of a vector n dot d mu of a vector n. So this would be just n1 up to nn. So it's like having basically capital N scalars, right? One is n1, one is n2, etc. Right? So this would be just, if it was like this, it would be just n free scalars, right? But there is a condition with the condition that this vector is unit. So that's what makes this theory very non-trivial. Right? Without this condition, again, n free scalars. With this condition, now we have a point on a sphere. Right? Now it tells you that n belongs to a sphere. Of course, the name is obvious, right? ON is just a symmetry. It's a symmetry that rotates this vector, and it's a symmetry of this action. Now, before and starting to think how would you go about tackling this model, let's think what could this model describe? Yeah.
Is mu going from 1 to 2?
Right. Mu goes from 1 to 2. Yeah. So x mu would be x1, x2. Right. Just Euclidean, flat. Okay. And by the way, you notice right away, since you are asking that, so you have two integrations, you have two derivatives, right? So naively, if this, again, if it was not for that n squared plus 1, it would be just n scalars, and this would be just a free CFT, right? We will just have n free scalars, and this still looks like a CFT. There's no scale involved. Under rescaling, right, d and the x cancel. So this is perfectly invariant. This looks like classically there is no scale. So this theory is classically conformal. Now, what could this theory be good for? So we could think that this theory describes a space that is two-dimensional. So I have a space that's two-dimensional. Let me draw a lattice. All right, so this would be my two-dimensional space. So this would be x1, and this would be x2. And then you would say that each point of your space, you would have a spin that is pointing in some direction, right? And you would have some vector parameterizing some spin in some statistical mechanical model. Right? And so here, you would have some spin n with fixed size, but with magnitude that could change. Right? And so this could be some 2D material. Right? Then the spins, they have the fixed size. There is an interaction between them. The simplest thing you can write is just dn squared that wants to keep them aligned. And then this would be the simplest possible action for a classical spin in a 2D lattice. Right? So that's one situation where this model could appear. It could describe a continuous spin, let me put spin in quotation mark, vector in a 2D material.
That is still not continuous spin. You still have only n elements.
No, continuous in the sense that the spin is not just spin up and spin down. It's a continuous vector that can change and can point in any direction. So if it was the real world, okay, let's put here a parenthesis. In this case, in our world, n would be equal to 3 probably, right? Because we would have at each point some 3D vector, some vector. Each point in the plane, you could have a vector anyway. It could be 2 as well. It could be 2. It could be maybe that the vector needs to be in the plane of the material, right? N equals 3 or n equals 2. You could engineer some material where you have some molecule that effectively behaves like an n equals 4, right? You would have to engineer something that would effectively look like it has some n equals 4 degree of freedom. You could try with some more complicated molecules, but this is one scenario where this would appear. Okay, another possibility, a different possibility for this, is to think that this n is a map from what? For example, let me think that this is x1, and this direction here is x2, right? And then for each point x1 and x2, you get a point in a sphere. So you take that point, here is a sphere, and to each point, you get a point here in the sphere. Right? And so if you have at fixed x2, at fixed time, if you ask what happens at fixed time, then at fixed time, you have some shape here in the sphere. What about at some previous time? At some previous time, this line here would be mapped to a different loop here in the sphere. And so what's happening is that I have a string that is moving in time. And so another context where this model, well, another way of thinking of this model is that this could describe a string in some Sn, in some n-dimensional sphere. In this case, we call this Sn, we call it where the map goes, it's the target, we call it the target space. And the cylinder, it's where it comes from, we call it the worldsheet.
Shouldn't this be Sn minus 1?
Yeah, probably Sn minus 1. You are right. Because if you have like two conditions, right, it's just x squared plus y squared equal 1 is an S1, it's a circle. All right. And so this could appear, then in this case, we could imagine n bigger. And in these lectures, later, in these lectures, we will encounter precisely this model where we will have strings in a sphere. Right? Can you guess what's the dimension of the sphere we are going to find? So in this lecture, we will find this, and then n will be equal to 10 would be an idea to have a 10-dimensional sphere. Infinity? No, it's not.
25?
6.
Only 6.
6. It will be a 5 sphere. Okay. We will see why a bit later. Okay. So this we will use this model will describe a 5 sphere. A part of the string theory. The string theory will have a sphere. It will have also some anti-de Sitter space, but this will later show up. So this gives us two examples of how there's two instances where this would show up. Now, let's think a little bit now, how would we go about studying this model? So, let me point out that first and foremost, this is a non-perturbative model. In particular, this model, as I will explain, is not weakly coupled. It's not trivial to just study it with perturbation theory. So how would you go about studying this model? So first, just to highlight how it is very nonlinear, let's work out what are the equations of motion for this theory. So there are two ways we could go about. We either trivialize the constraint n squared equal to 1, or we live with it. Which one do you prefer to do first?
The first one.
The first one.
Which one was the first one? I forgot. Trivialize the constraint? Okay. So there are two ways of doing. So one way is we solve n squared equal to 1, for example, by writing that n is equal to some component pi, and then here square root of 1 minus pi squared, where this vector pi has n minus 1 components. Right? You agree that now n squared is automatically equal to 1, and we are just expanding around the north pole, say, of this sphere, and we have some tangent vector pi, and then the other component has to be fixed to be this. And so you see that now, if you plug this into the kinetic term, d mu n square, this derivative, right, will give me what? The derivative of the first term, it will give, or let's do first the derivative of doesn't matter, they're all similar. So yeah, the derivative of this first would give me del pi dot del pi, right? I just take this n minus 1 components, and then the derivative of this term would give me plus, let me maybe write explicitly what it would be. It would be something like 1 over 1 minus pi square. From taking derivative of a square root, you get 1 over square root. You do it twice, you get 1 over the argument of the square root. And then you get, let me write explicitly, pi index A del mu of pi index A. That was from derivative of 1 pi square, and then pi index B derivative with respect to mu pi index B. And so this would tell you that you have n minus 1 massless fields. Right? And now this stuff would give you infinitely many vertices. Why do I say infinitely many? Because expanding this 1 minus pi squared in a geometric series will generate pi squared, pi 4, pi 6, etc. And so we will have an infinite sequence. The first vertex would be just what is written here. I can draw it like this. I can say that the index A goes like this, the index B goes like this, and the derivative is 1 in the leg A. This would be the vertex. Plus, then the next term with an extra pi square would be something like this vertex, the same thing with the derivative here and here, and an extra line for pi square without derivative, plus, and then there would be the term, the next term, whereby these lines like this, I follow what the color of the index is, and then I put an arrow to indicate the derivative, plus dot dot dot.
What do you mean when you don't make a vertex and just go that way? In the first diagram, say.
This?
Yeah. Why didn't we?
No. I just, they are interacting here at this vertex, but I just don't join them to indicate that the line A goes here. A is connected to A, B is connected to B. So to follow the color index, I keep the lines a little bit open. So here, for example, C goes to C, A goes to A, B goes to B, but they meet in a 6-point vertex. And so you have all these infinitely many vertices, and so your equation of motion in this case would be box pi equal to an infinite set of vectors. Right? Just the derivative with respect to pi of all these terms, etc. And so it's a complicated type of equation. It's not one that you would solve in a trivial way. It's possible to write all this as a finite number of terms if we learn how to live with n squared equal to 1 instead of trying to trivialize it. So let's do it that way. Yeah? So this is one way. where we get that this theory, it looks like at least now you know how you would work with this, right? You would start with these n minus 1 massless fields. You would have all these vertices, right? And you would now start doing perturbation theory, and you would hope that you would be able to resum it and to converge. But at least you know how to do this with this, with this, with this, right? At least now you have perturbation theory, you have Feynman diagrams and so on. I would claim that you will not go very far, because as you will see, the theory flows to a strongly coupled point. So this will tell you only about the UV of the theory, but that we will see later. But at least for the UV, you could do this. You could study the theory like this. Okay, to study the ultraviolet behavior of the theory. Okay, so let me already anticipate that this would be useful in the UV. It's not obvious yet why, but that will be the conclusion of the lecture, that in the UV, indeed, it's good to keep this and drop the rest. In the same way as in the lecture, remember, when we have a massive scalar, in the UV, we go to a massless scalar, right? And then when we go to the infrared, we go to an empty theory. Here in the UV, this is what matters, and we go to n minus 1 massless scalars. So that will be the conclusion indeed. So in the UV, we can go there, and then we have the massless scalars plus a small perturbation, and now we can do perturbation theory. But if we want to go to the IR, that's not good at all. So that's one option. The other option is we live with this, which means that we have to write our action, which was dn square. Right? And then we want to add a Lagrange multiplier that is a constraint that sets that n squared is equal to 1. Right? So how do you add constraints? You add plus lambda. Lambda is a new field times n squared minus 1. If you want, you can put an I here. Do you like with an I? It's just that with an I, it reminds you that e to the I lambda, if you integrate of e to the I lambda x, if you integrate over lambda, gives delta function. Right? And so this looks like a functional delta function that sets n squared equal to 1. Okay? And now our action is an action for the field n and for the field lambda. Okay, so now let's write the equations of motion for this. What are the equations of motion? Well, I take the usual Lagrange equations, box of n, right? From here, derivative with respect to mu of del mu of n is box of n. Do you agree? Equal to the derivative with respect to n, which gives me I lambda n. So that's the variation with respect to n. Correct? Just like if this was m squared, here you would get m squared n. Variation with respect to lambda gives me n squared equal to 1. Right? So this would be the two equations of motion. This one is variation with respect to n. The second one is variation with respect to lambda. So how do you put this equation in a computer? How do you solve this equation? Doesn't look good, right? Because n squared equal to 1, fine, I can start with some n squared equal to 1, some configuration. Then I want to evolve it, what's lambda? This equation of motion look a bit funny, right? They don't look very good. What should we do next? How can we transform this equation into something a little bit better? How can I find lambda? That was the goal. How could we try to find lambda?
We try to square the first one, then use the condition the second.
Good idea. So let's multiply the first equation by n. Then if I multiply the first equation by n, I get n dot box of n equal to I lambda times n squared, which is just I lambda. And so, and I can do even better. Because notice that n squared equal to 1. That means that derivative with respect to mu of n dot n equal to 0, right? And that means that n is orthogonal to the derivative of n. That makes sense, right? You have a unit vector, so when it changes, the variation is perpendicular, right? So that's obvious, right? I have a unit vector. The change of my vector is always perpendicular to it, right? Because the vector is unit. And that means when I take one more derivative, that n dot box of n is equal to minus derivative of n squared, right? If I take one more derivative, I get derivative n dot derivative n plus n dot box n equals 0, and so I get it. And so this factor here, n dot box n, is minus del n squared. And so finally, the equations of motion would be put here in a box. Box of n equal I lambda becomes this, I lambda, and put all in the same side, plus del n squared times n equal to 6. Right? This would be the equations of motion. So you see there's no parameter, no weak coupling parameter, right? If you have a solution n, rotation times n is another solution, so you have ON symmetry. And it's nonlinear. There is n, and here there is n cubed. Right? So it very well motivates the fact that it's a nonlinear sigma model. And so these equations are quite non-trivial to solve. You cannot solve them in perturbation theory, right? So it's not like box phi equal to some perturbative potential that you know how to solve order by order. And so here you would have some very non-trivial. So this is a non-trivial dynamics. Turns out you can solve these equations, but you need more powerful techniques. But again, what I want to emphasize here is that this is not just some weakly coupled model. Okay. So we'll try to think of this model by thinking of normalization. So we'll try to see what would happen to this model if I were to apply normalization. For example, in this spin picture, imagine I coarse grain and I join blocks of 4 spins into some effective block. Right? So I start to zoom out, and now I don't see so many sides. I just zoom out and I integrate out fields that change too quickly. Okay? Or in my picture of my string, I start resolving the changes of string at some very small scale, and I only see strings that change at a longer scale. So the idea is, as usual with normalization, what we are going to do is split our field n into a fast part plus a slow part. The slow part is all we need. It's okay for low energy or for long distances. And then these fast modes, we integrate them out. In other words, the theory that describes the slow modes, when I ask physical questions in that theory, I must get the same answers as the questions I ask if I keep the slow and the fast modes, if my question is about low energy. Right? So if I ask, what's the correlation function between a point here and a faraway point here? The result is the result, and it's the same whether I integrate out super high frequency or not. But if I ask questions about UV, what happens when I bring them very close? Then if I bring them too close, I need the full theory. I cannot just ignore the fast modes. Right? So these ones we can integrate out if we care about low energy or long distance questions. So the idea in more detail is to start with your action or your vector n, which is exponential of minus 1 over this E0 square times the Lagrangian for the integral of the Lagrangian for this vector n. Sorry, no. Let me just write like, sorry. Let me say, how did I say? The Lagrangian, I did not define. Okay, so e to the minus the integral d2x times Lagrangian of this vector n. Right? And then we want to integrate out. We want to integrate over all configurations n. Okay. All modes. So let me write like this. It's an integral of a product of dkn where I integrate out the momentum so this was the original cutoff, and this is now the new cutoff. That is, I started my theory, and my theory already comes with some level. I know that I cannot go beyond the 1 nanometer. If I go beyond 1 nanometer, I start to see the molecules and so on. I no longer see spins. So there is I start with a cutoff, like 1 nanometer, right? But now I say, oh, but the questions I ask are going to be questions about 1 meter. So I can increase that cutoff from 1 nanometer to 1 centimeter. There's no big deal, right? I will get an effective theory that I cannot go beyond 1 centimeter. Fine. I only care about longer distance, right? So I want to integrate out the physics between 1 centimeter and 1 nanometer to get my effective theory. So I start with some original cutoff, and I want to go to a new cutoff, which is this, right, in position space. Then this integration defines for me a new after I integrate, I get e to the minus an integral of a new Lagrangian d2x, which is the Lagrangian that describes the effective low energy dynamics that remain after I integrate out the fast modes. What will this Lagrangian be? Just by symmetry, it will be similar to the original one. It will be something like 1 over 2 E0, let me put some tilde, square, times dn square. That's the simpler thing it could be, right? If lambda tilde is equal to lambda, it is just this. And then, what else could I generate? Whatever I generate that has ON symmetry, there could be plus some constant C1 times, say, some d mu n square plus dot dot dot. So here I write, when I integrate out, I generate whatever has the right symmetry. Right? Anything that has the right symmetry would be generated upon integrating them out. Now, this stuff here, for example, with more derivatives, this has 4 derivatives, and so these constants here, what are the units of length of these constants? What's the dimensions of this constant C1? So this C1, the dimension of C1 is equal to, in units of length, what is the, how many length powers? I have 4 derivatives. Careful. No. Why 4? No, not 4. So again, let's see. This has 2 derivatives and d2x, so it was cancelled, balanced, and this is, there's no dimension. Now, here we have 4 derivatives in total, 2 integrals in x, so how many lengths do we have here? 2. Right? So this is length square, in other words, is energy minus 2. Right? And so these terms here are what are called irrelevant. They come with positive power of length, and so they don't matter at low energy. Right? So these terms here are what we say they are irrelevant in the infrared. Right? Let me just recall what's the usual way of understanding this. So how would they show up in a physical quantity, right? Suppose I'm computing some physical quantity, some probability of whatever. And then there is the effect of C1. Right? Some process probability of whatever that happens at energy E. Now, this C1 here has dimensions of energy minus 2. So to get some physical quantity, this will come multiplied by E squared. Just by dimensions. Right? And so it goes to 0 for when the energy is small. So these are what are called irrelevant terms. So when the dimension is positive, at low energy, these should not matter. The only thing that can matter is this. I mean, that's why universality is so powerful. Because if you have a vector n, you write this type of interaction, and that describes our magnet. But other lattices would generate, when I expand the interactions, will generate such terms, higher derivatives and higher and so on, right? We are just expanding some discrete interaction in derivative, second derivative, third derivative, fourth derivative, etc. And it should not matter at low energy. Otherwise, we will need to know all the details of all the molecules in a table to know the properties of the table. Of course, we don't. Right? Because they are irrelevant. At low energy, it doesn't matter. Okay, good. That's good news. And that means that what we really care is about the first term. Right? And so our goal is to study this E0 tilde. Right? Our goal is really this guy here. Right?
We have 4n but 2 derivatives, components like that we wrote for preservation. Those terms are also symmetric, right? Like there are 4n but 2.
Right. But you have to be careful that here it was in this pi-n language with a pi vector. Now you could think if this was n square is 1, so you cannot have this.
No, but what about the rest, this part?
What about this? This is 0 by what we just saw here.
Oh, yeah.
So you can also not have.
Also, I have another question about the quantization. In string theory, we sometimes don't put the constraint at the first place, make the Hilbert space bigger, and define a physical space by constraint quantum mechanics, right?
Yeah.
So why we cannot do the same thing here? Like go in a bigger physical space and ask the physical state have that condition. Something like both covariance.
Be careful. In string theory, we do it at the worldsheet level, not target space. Right? So we say in the worldsheet, in the 2D theory, I don't want all, so I don't take all the states. For example, if I have a state that has momentum, which is longitudinal, that rotates, I remove that. because that would describe a string that is rotating, and if I see the string rotating, I cannot see it's not moving. So I mod out by states that are doing something on the worldsheet, not on the target space.
But also the constraints are similar to this, like the constraint on the target space, right? The energy momentum. Oh, okay.
No, they are worldsheet conditions. They are conditions on, there are some operators that act on the states with a fixed target space and remove some states. They don't change the target space.
So in general, the trick that we do, like BRST and this stuff, doesn't work in this way?
No, it doesn't, no. Oh, for this one, there are no cheap tricks to quantize this model. This is a tough model, and remarkably, we know a lot about this model, but there's no trick of starting with a nice Lagrangian and doing some simple manipulations at the level of the Lagrangian and getting a solution. Good. So now, let's then do this separation of fast and slow modes. So suppose I want to decompose my field, and I say that I have some vector n, right? And my vector n is changing slowly. So let me consider some n0. This n0 is slow. So I have some slow field that I consider. Let's consider one configuration, right? Now, at each n0, you can now define some kind of tetrad. You can define some vectors here. EA, which will also be slow because they are related to this vector n0 by being orthogonal to n0. And this EA would obey that EA dot EB is equal to delta EB, and that EA dot N0 equal to 0. And now we would parameterize a general solution for the vector n. So let me write it and you see if you like it. So there would be some n0, some slow vector. There could also be some EA, this vector's EA, with some summation over A. You see that from the point of view of components, I have all the components, n0 plus n minus 1 of these guys, I have a basis of my space. Right? So this is enough to describe anything. And now here, I can multiply by some phi A. And then, because of these conditions, if I compute the square of this vector and I want this to be normalized, this guy should be multiplied by square root of 1 minus phi square. And now the claim is that these phi now are the fast variables. These guys could be fast.
How are we defining slow and fast in this case?
Slow and fast we defined by this. We consider some configuration of n that you would parameterize with momentum smaller than lambda tilde. So you have some configuration of n0 where if you were to decompose it in momentum, you would only see momentum up to lambda tilde, below. Right?
So we are doing some kind of Fourier transform.
Not from, we are just saying, let's take some n that changes, whose typical change is only at scales bigger than some inverse of some k tilde. If you want, you can Fourier transform to be more rigorous, but it's not crucial for this argument. So that defines what n's do you allow as backgrounds. Then this, by doing just this, now you define an n-dimensional basis. You have your n and you have the orthogonal to n. Now any vector, in particular the fast modes, can be described in this basis. So we just put that phi, and that phi now is going to be the fast modes. By definition, because turning the phi's off already describes the slow mode, right?
Means Like here you're assuming that n0 is a slow mode.
That's right.
So
Because that's what we want to do. I'm just writing this naive equation in a rigorous way when we deal with a field that is on a manifold. So I cannot just say n is n fast plus n slow. Because then if n slow has n squared equal to 1, I add n fast, I don't no longer have n squared equal to 1. So I need to do it in a smart way. So that's the smart way. Right? That's just a deformation that keeps me in the manifold. So for that, it's useful to have these tetrads to make sure that I'm always on the manifold. Good. So then we have this condition here. Now, let's write now a few simple equations. So the goal is to plug now this n into our action, right? Now the next step is plug this n into the action. But let's do it a little bit slower to practice a little bit how we will do it. So first we notice that any vector can be decomposed into this n0 and EA. I feel like probably I should put some, it's probably better to put some vectors. Let's do it. So any vector n I can decompose into these vectors, right? N was just one example. So I can also do it for d mu of n. Right? D mu of n, I can also write it. Now, d mu of n will have components in the direction EA and components in the direction n. What can you say about those in the direction n? Are there components in the direction n on the right-hand side? No, right? Because imagine it was there. You dot the equation with n, and that term would survive. The EAs would go to 0. This also goes to 0 because n dot en is 0, like we saw before. So there's no term with n. So there are only components in the tetrad direction, EA, right? And that whatever the coefficients are, we can call them some BA mu, and we have sum over A. Okay, so now we learned how to take derivatives of n. How do we take derivatives of EA? Well, derivatives of EA, it could have both terms. So it can have some terms with EB. Then there would be a sum over B with some A mu within this AB. I'm not worried about A up or down. They are Euclidean. EA up is EA down. Don't worry about it. It's the same. So this would be one possibility, right? But now it's not the only one because EA can contain n. So I should also add a term with n. And that term is minus B mu A times n. Now the fact that it's the same term that appears above is not obvious. The fact that these are the same follows simply from using equations like n0 dot EA is equal to 0, and therefore derivative of n0 dot EA must be equal to minus n0 dot derivative of EA. And if you do it, then you figure out that that coefficient B is not new. It's the same as what appeared before. Okay, so we learned how to take derivative of our directions. Now we can just take derivative of this expression. Derivative with respect to mu of our vector n. Sorry, you should have corrected me here. What is wrong here? n0 and 0. So now we know how to take derivative with respect to n. We can now take this derivative and let's group things like this. Let's say there is something times n0 And then there will be plus something else times EA sum over it. So let's see. So who is proportional to n0 when I take derivative? So look here. So the derivative, if it acts on n0, no. But if it acts on the square root, you still get n0, right? So derivative acting on square root would give me, well, it would give me derivative of square root. Times n0. Then the derivative acting on phi a is not proportional to n, but the derivative acting on EA would give me this term. So I'll get minus b mu a phi a. And those are the only terms proportional to n0. Proportional to EA, if the derivative acts on n0, so I get square root 1 minus pi squared. If the derivative acts on n0, I do get some b mu a. If the derivative acts on the phi a there, I get plus b mu phi a. And if the derivative acts on the EA, I get plus a mu a b phi b. Cool. Now this is very good. We are done now, because now our Lagrangian is, of course, just 1 over 2 E0 square times the first square bracket square plus the second square bracket square. You agree? Because n dot dot is 0 is equal to 0, so I just square the first one and I square the second. Or more precisely, I sum over the second one square. Good. So we managed to plug slow plus fast inside the Lagrangian. Now we have to integrate out fast. That's what we are going to do now. So let's write it. So the Lagrangian, let's now write up to quadratic terms in phi. So we expand in the small fluctuations phi and we work out up to quadratic terms. So it's equal to what? So first the term without phi. So if I said, if I don't have any phi, it's this term here, right? This b, this is the term without any phi. If I set phi to 0, everything would go to 0 except this term here. So that's the term without phi. So let's write 1 over 2 E0 square integral d2x b mu a square. That's the term without phi. Sorry? Over this E0? No, I'm just plugging in the original Lagrangian, right? The original Lagrangian, the starting point at E0, and I plug there, so it's still E0. Right? The goal is to find E0 tilde, is to find that at the end of the day we will generate we will change this E0. But for now we are just plugging it, it's still the original one. And now the quadratic terms that can come from this square bracket or this square bracket. So let me write it down. Plus 1 over 2 E0 square integral d2x. And now there are two very cute terms. One is del mu phi A plus or minus A AB mu phi B square. Repeated indices are summed over, of course. And the other term is plus B mu A, B mu B times phi A, phi B minus phi squared delta AB.
There won't be any linear terms because B mu there has power 0 and there are linear terms, so somehow they cancel out.
There are no linear terms. Where would you like to get linear terms from?
Say when you square something, you have two AB term, and B mu has some phi 0, maybe phi power 0 contribution. Say A mu has linear in phi. When you take a product, they should give a linear term.
Yeah, there are none. There are no linear terms. The action must be invariant under phi to minus phi. But okay, it must be a trivial question of computation. This result, what I wrote in the blackboard, is correct. Okay, so now notice that the fact that I have this term here, this d mu phi square, this tells me that phi A is a massless field with propagator. The propagator phi A, phi B is just what? It is just delta AB over p square. I'm doing now momentum space. And because it comes multiplied by this 2 is 0 square, there is some E0 square here. That's the propagator for this fast mode. Correct? Now, this is when you ignore this gauge connection. Right? So with the gauge connection, what you have here, so this is the propagator following from box phi. But here, what you have in this parenthesis is something like a covariant derivative of my field phi A squared. And so you would also have interactions with this field A. Okay? So we ignore A for now. We ignore A for now. And we can ignore it. And I will explain in a second why we can ignore A, but for now, let's ignore A. And all we take from this first term is that phi is a massless field with propagator 1 over p squared times E0 squared. Yes?
Doesn't the B term effectively give mass to the phi? Because we have a phi squared term there in the second bracket, right? In the action for phi.
This B is not a constant. Now I'm going to treat this as a perturbation, and we are going to see what this gives. Now let's see. Let's then focus on analyzing this term. How do we analyze this term? This is a small term in the action. I bring it down. I compute the expectation value using the propagator, and then I put it back up. You agree? So now we analyze the b squared term. The b squared term, when I bring it down from the action, we get 1 over 2 is 0 square, b mu a, b mu b, times the expectation value of phi a, phi b, minus phi square delta ab.
Here we are computing the b squared by that, what do you the expectation.
I want to compute this term here. I want to integrate out to phi. Right? So I want to integrate out phi. So I bring it down from the exponent. I integrate out phi. Phi is a Gaussian field with this propagator. And then after it's integrated out, I exponentiate back again to see what effect does it have for B, my slow field. That was the goal, remember, to find the Lagrangian for the slow fields. Okay.
Yeah.
Right? So we want to bring down, integrate out the fast field, and bring up to get the Lagrangian for the slow field.
Yeah.
Okay, good. So what is this quantity here? So this quantity, you see, as far as indices go, it's delta AB from this guy. And from this guy, there is a delta AB as well. But there will be 1 from this term. And here from phi squared, there is a factor of n. So I have this phi squared. I'm doing a propagator. And there are n options for the second term, right? Phi 1, phi 1, phi 2, phi 2, phi 3, phi 3, etc. So 1 minus n times the integral d2p over p squared times E0 squared. 10 more minutes, please. And so all in all, what do we get here? This cutoff, we integrate, like we said, from some cutoff lambda tilde up to lambda, right? Okay, to be more precise, if we are doing things correctly, there is a 2 pi square, right? Always. D2p over 2 pi to the d, and within Fourier. And so in total, we get E0 square cancels E0 square. Delta AB just gives me B mu A square when I have the delta AB. The E0 square cancels. Now the D2P, let's see, D2P is R dr d theta. Theta gives 2 pi. So there's an extra 2 pi from this. So it kills 2 pi from here. And so I get just 2 pi. With that 2, it gives me 1 over 4 pi in total. Times 1 minus n, or let me write it as n minus 1. But if I write as n minus 1, then the integral over the radius, that would give logarithm of this over this, would be logarithm of lambda tilde over lambda. As I flip the sign, I also flip here the arc. Correct? And so this is the result. And so my action becomes, now I put it back in the exponent. And so we get 1 over 2 E0 tilde square times the integral of exactly what we said we would get, our original action square, where 1 over E0 tilde square is equal to the original 1 over E0 square, plus this extra term that we got, plus n minus 1 over 4 pi. Is it correct? All the zeros cancelled. No, and log. Lambda tilde over lambda. Right? And so we generate.
That whole term should be multiplied by 1 by E0 square also.
No. No. There was E0 square here. And the propagator had an E0 square. And so in total, there was no E0 square. Okay. I confess I'm a bit confused. Ah, sorry. Okay. This is 2 pi, 1/2, right? So, right. So, because of this factor of 2 here, if I want to write the correct equation here, it's 2. Right? If I multiply everything by 1/2, I get what was originally there, this, what was originally there, and then the 4 pi that we just computed. Correct? In particular, this implies, let me remind you that this tells us that, so this is our new coupling after we flow. And in particular, it's useful to write it in the following form. This equation, you can easily see that this means that the derivative with respect to logarithm of the cutoff of 1 over E0 square is equal to n minus 2 over 2 pi, right? Or, equivalently, that the derivative of the coupling of E0 square with respect to the logarithm of the cutoff is equal to minus n minus 2 over 2 pi times, in this case, the coupling to the 4. And this is what is called the beta function of the theory.
Why is it n minus 2?
Why is it n minus 2? Good question. Because I did a mistake here. There is a mistake here somewhere. Help me out. Where is the mistake? So this guy, the expectation value, gives delta AB. Right? How many fields phi there are? N minus 1, right? So this is not n. This is n minus 1. Right? From this term here. Right? Phi 1, phi 1, phi 2, phi 2, phi 3, phi 3, up to n minus 1. And so it was n minus 2 here. And this minus sign here is crucial. This minus sign here that we just got is what is called asymptotic freedom. So what this means, what this sign means, is that the coupling vanishes at high energy. That's the freedom. You go to the UV and this coupling effectively vanishes. And that's why in the UV we go to n minus 1 free scalars. Right? We started in our theory, we wrote that language there, but if the coupling goes to 0, right, after you rescale pi, it means that all these vertices you can ignore and you go to n minus 1 free scalars. Right? So here, now we know that we get n minus 1 free scalars in the UV. But on the other hand, the coupling grows at low energy, and so we have strong dynamics in the infrared. The physics is strongly coupled and is non-trivial in the infrared. exactly as for the real world, where when we have free young meals, pure young meals, at very high energy we get free gluons. At very low energy we get some non-trivial dynamics of glue balls, and we get a mass gap, and we get a very non-trivial theory. And so that's why this minus sign is so great, and why people love this theory so much. Like a toy model for four-dimensional chromodynamics, which also has asymptotic freedom, as I'm going to recall in the next lecture, in the beginning of the next lecture. So, I'm sorry for going over time, but just to conclude, and we will summarize again in the next lecture, let's make a few comments about this final result. So the first result is that we got indeed the form of the action we expected, compatible with symmetries, right? It was this term. And then we said we could get irrelevant terms as well. And we would get irrelevant terms, but we don't care. We only care about the low energy, right? We want to see what happens at low energy. The A field is one such example. And it's a beautiful explanation why. You see, you could imagine, what about this A field that we ignored? Why is it okay to ignore this A field? And you see, first notice that A, what are the dimensions of A? We can look at A, how A appears. So A has dimension 1 of length, right? Or minus 1. Because it's multiplying EA, and its derivative of EA equal A times EB, right? So it has the same dimensions as taking a derivative, right? So A is like, it has dimension of 1 derivative. Now, A is appearing here like a covariant derivative, right? A is effectively giving a covariant derivative of this scalar. And so when you integrate out of the scalar, you will get a gauge invariant quantity for this A. Because A, you can think of it really as a gauge connection, the way it appears in the action. And so when you compute the effective action, this A, what it will generate is something like F mu nu squared. That's the first term it will generate. It's the first gauge invariant operator you could get out of the gauge potential. But A has dimension 1 already. You take one derivative to make F, it has dimension 2. You square, it has dimension 4. Right? So this guy has dimension 4. So it's irrelevant. So you don't need to worry about it. That's an example how this, that's why this torsion, this A you can think as a torsion of this tetrad, you can just ignore it. Second comment is the n minus 2. This n minus 2 means the beta function is 0 when n is equal to 2. But that's fine, because when n equals to 2, if you parameterize your vector for n equals to 2, if you write your vector n as just cosine theta sine theta, your Lagrangian becomes just d theta squared. And indeed, the theory is free. In other words, a sphere has curvature. And so the theory on a sphere is non-trivial. A circle is too trivial. Circle is like flat. You just identify it, nothing more. And so indeed, the Lagrangian would become 1 over 2 is 0 squared times this. And indeed, this has beta equal to 0. So it was a check that we did no mistake. Or rather, a way of fixing our mistake that we did there in the middle. Right? It has to be proportional to this n minus 2. Indeed, for n minus 2, there is no running of the coupling. So in the next lecture, I will summarize a little bit what we did. And now that we got the beta function, we will ask, what does it imply? And so if we only know the infrared, what is the UV? What happens in the UV? In the UV, sorry, the opposite. If we know the UV, what happens in the infrared? In the UV, we say we have n minus 1 free scalars. And then when we go to low energy, what happens? What's the dynamics and what is happening there? That's what we are going to finish next time. So that will be the goal of next lecture. Okay, so let's take questions.
I was just going to ask, is the reason why it's consistent to only go to second order and phi because all the higher order terms are irrelevant? So that's why we only have to worry about quadratic.
That's true, but what you can also do is you see that what we did here was compute an effect of a fluctuation, right? And so you can ask, is this fluctuation small? And so you can estimate. So this will be a good approximation as long as this term here, which is this log, is, so this is the new term that you generate. If this new term is much smaller than this, then your approximation is good. So you can just, you do a small step where lambda tilde and lambda are like lambda tilde is 1.1 times lambda, right? Then this is order 1. This, we started with something very big because this was coupling is small, so this is very big. So this is okay, and now higher powers, you will easily see that they will come with extra powers of E0, so it will be more and more suppressed. So for the purpose of studying the flow, you derive this equation. It's a good approximation because this is much smaller than this. Then you study what differential equation does it imply for the flow of beta. It's here. And now you start with the beta function and you ignore where it came from and you know the flow of the theory. At least close to the UV, and it gives you an idea of where it is.
Well, I guess that's just what I was trying to understand. It's like, sure, close to the UV, we have this minus sign, but if we get too far away, how do we know that, like, it will change or go positive or something? But I kind of justified it to myself that won't happen because the extra terms are irrelevant. So it will be less and less important as we flow down.
Right, so here all we know is the UV. The infrared dynamics, we don't know. It could be that there could be another fixed point later. We will show that there is not. We will argue that what happens is that you have dynamical mass transmutation and you will quantumly generate a mass. But just from this trivial argument, you don't know. All you know is that the beta function starts negative, but then you don't know what happens, right? This. So here you know that if you start with some E0, you flow to E0 equals 0. Right? But then you don't know if later there will be a new 0 or if it will continue to go forever. This is much harder to know.